Right, so we're gonna find out if this worked. I've got the wireless mic. I've got to just pull this up. This is the first time we're streaming with an actual mic in here. Look at that.
I've got to just pull this up. This is the first time we're streaming with an actual mic.
It's working. All right, we're a little bit distant, so I'm trying to set up in here so it looks nice on camera. The problem is we got to get the giant TV to be. Once we get this kind of, how I want it, I'll mark on the floor where everything goes with some tape. That way we know where to put everything. This battery's dead, so I got it tethered to the thing. Let me try zooming in a little bit. We might just have to crop some of the screen. Maybe like that. That's all right. So I gotta get everything kind of at an angle. I might have to tip the table at a little bit of an angle here too, but I was gonna go, running here? Okay, we're good there. So I was gonna go over a couple of things with you guys. Unfortunately, I don't have my stand that holds up the tablet. Yeah, see, this will work. We just gotta pivot the table a bit. So we've been trying to set this up as kind of like a nice broadcast studio over here. I was going to move the inventory shelves, but I'm going to put more inventory shelves, and actually I'm going to leave them because it's kind of a cool backdrop once we organize it. And we've got this giant, like 600-pound table, and we're going to talk about that in a minute, because Paul saw our shitty little cart over there and said he didn't want his name on that piece of shit. So he shipped us a $2,000 table. So everybody thank Paul and Scientific Sales for buying us this over-engineered piece of equipment here. It's a stainless steel 6-foot by 4-foot table, and this thing is so heavy. Yeah, let's put it that way. So you could put an elephant on this thing. So this is gonna work out really well for a lot of things. So everybody thank Paul. So I think what we're gonna do is probably rearrange things a little bit so that we can tip this a little bit to the side. But for now, it'll work. So we're going to go over a few things because I've had to change some things, and let me go get my laptop. I've had a couple of challenges here that have popped up. Hopefully the mic stays connected. If not, it'll come right back. I got to go in the office. I forgot my laptop because I want a way to see the chat. Actually, no, I don't, because shit. As I say, I gotta unplug it. I'm just gonna have to unplug it. So a little bit behind the game here today.
A little bit.
Okay. So what's cool is with the setup we're running, so there, get that off of there. So we can actually go to camera 2. And this might take a second to load because I don't have the latency settings and everything figured out. So while we're doing stuff on the table here, we've got camera 2. So for example, if we're working on something, I don't know, Raspberry Pi or something, and trying to get everything set up, we can actually, if we're going to work on something, we can top down it, which is pretty cool. Lots of adjustments here. So we can really zoom in on things, and then I've got it set up so we can actually draw on the screen. I just don't have, I need my Apple Pencil. I have an Apple Pencil, I don't know where it went, but let me make sure we still got sound with this one.
Green, I just
Yep, we do.
I need my Apple.
So we got that, so that's cool. So we got that shot, which is going to be helpful too for launching and preparing balloons and such. So I'll try to get this set back up where it was. So that's kind of a cool way to do it. And of course we still got the big wide shot up there. So I'm just kind of trying to test everything out. I figured we'd go live and answer people's questions or something. So I'm sure people are going to have them. We still got sound on this one? We should.
We'd go live and answer.
Yeah, we do. Okay, so I'll show you guys a couple of things that have come up. One of the things that came up yesterday, last night, was I started running into a problem with, God, this table makes me look really small, doesn't it? Like, I need something to stand on. Like that. I don't like that. I feel small. I don't know. I like the table though, no complaints, but anyway, I got some stainless steel cleaner. You guys got to let me know what I need to use to clean stainless steel because the fingerprint magnet. What I'm actually going to do is I'm going to get a foam, like a big foam pad to put on here, so when we're doing stuff, we're not screwing up the top of the table. Because the main reason is we can actually run inflate balloons on this. Speaking, we'll do some product placement. There we go. But anyway, folks, so last night came up with a problem. I showed up here at like 10 o'clock last night, and I had this kind of last minute thought, and I was just like, oh no. Well, it turns out we have a problem. So I fixed the problem, and I'll show you here. But there's a couple of things that are new, and if you look at the screen up here, I'll adjust some settings on this and adjust the bit rate so that you guys can actually see the smaller print on the screen. One of the things that we're going to do when we're actually doing a live stream in here is I need to turn off the lights up here, and then we'll just run some actual studio lights, which I have on the way. So it'll make things a little more natural, and you'll be able to pick out the text on the screen. But when you go to our website, for those of you that don't know, you're just seeing my iPad screen right now up on the TV. There's this widget on our website right here that shows all the soundings. There's now a little button on them next to each sounding that's a little blue info button. If you click it, I know it's probably hard for you to read, but there's a comment for every single balloon launch based on, like, for example, the one in Mississippi, it comes up, says balloon launched in rain, light to moderate intensity, shunted the ascent rate. Most of the area was in a large rain shield, 200-gram balloon, no parachute. Those are just notes that are mainly for us, but we're sharing them with you because, I mean, it might be interesting, but it's kind of for us to say, hey, if we need to make some notes about this for whatever reason, that's how we can do it. So that's new. That was a byproduct of what I was actually doing last night, which was where I found out that our API is a pile of shit. And I fixed it. It's not a pile of shit anymore. So I sat down from it was probably about 10:30 last night to about 5 o'clock this morning in my office getting this done. And yeah, we got it done. So we'll go to the whiteboard here. So I'm going to explain to you guys just a little bit, and I'm going to be able to see, I can draw up there. See if you guys can see that very well. Yeah, you can. Ooh, maybe not. Yeah, you guys can see that just fine. Okay, how do I erase? There we go, just like that. We could go over there to the whiteboard, but that would mean I would have to move. So there's a couple of different components, obviously, to what we do. We've got our ground station receivers and then the radio sonde, like this, that sends the signal to the receiver, and then the receiver sends it to the internet. So I'm going to give you guys a little bit of a map of how we do this so that it kind of makes sense how we do it. So we've got our weather balloon up here with our radio sonde. That's floating around doing whatever, all right? And then down here we've got our, I'm just going to draw a little triangle with I don't know. That's our ground receiver, okay? Use your imagination, guys. I'm not an artist. And between them, we have a radio link. And we're going to talk about, and I'm going to write this down because I'm going to forget channel. We're going to talk about channel spacing and channel coordination with this too, because this actually gets into some RF engineering as well and logistics. But anyway, so we have an RF link here. So that's a radio link between the balloon and the receiver. And then over here, we have our server. S for server, I don't know, whatever. And between the receiver and the server, there is a cell tower of some sort somewhere. We'll call that our cell tower, I guess. I really wish I had my Apple Pencil. So that's our cell tower. And between the ground station, I'll label that ground station, and the cell tower is, well, it is radio, it's RF, but we're just going to say LTE for plain and simple. So we're going RF radio frequency from the balloon to the ground station, and then LTE from ground station to the cell tower. And then the cell tower goes through the internet, however it's going to go. We'll just call it web, to our server, which is this thing over here. From the server, that's where it processes everything, and then that's where you go to our website, like right here, and you click on, let's say, the sounding or the tracker, and this is where you guys view the tracker, and that you're pulling it off our server. So yes, we are going through Cloudflare with edge servers, but the API data comes directly from here. So no matter where you are in the world, when you load up our website and look at the viewer, you are basically in a direct communication with the server, which is literally right over there. So that's kind of cool, I think, anyway. But this is basically the map of how it gets to you. You guys are in green. You guys connect to the server via however you're going to connect. So this right here, that's basically how this all works. So in case, like, 'cause I know I'm pointing at a screen that you can't see. So balloon to the ground station, which is on the truck or is portable. That's RF. It's 400 to 406 megahertz. Ham radio operators, I don't want to hear it. We're going to talk about this in a minute. And then we've got LTE from the ground station to the cell tower. Now, the reason that we don't do LTE on the balloon, it wouldn't work. It's plain and simple, it just wouldn't work. And then the cellular connection takes it over fiber somewhere, and it comes into our server. And that all this crap happens in under 2 seconds. So the second this thing, the balloon and the sonde will receive a temperature reading, and every second it's sending a new data packet. It takes 1.8 seconds on average to get a temperature reading from the sonde to the ground station, packaged to the cell tower, and then relayed through a bunch of routers somewhere to our server. The reason it takes a little bit more than a second, even though we can do these in milliseconds with low latency internet, is because that connection, or the ground station packages the data, and it makes sure the data is valid before sending it on. So we're not sending known bad data. So it basically holds it for a second, buffers, and moves it. So every second it's sending a new data point, and then it takes about 800 milliseconds on average to go through and then get processed by that server, sorted, and then published to the API. So that's actually pretty cool when you think about it. We can get that latency down. We can make it faster, but we have to run algorithms to do a lot of what we're doing, and you have to put it through algorithms, and you have to queue it. You can't just do everything at once. You have to go step 1, step 2, step 3, step 4. You can't just blast it out. So like step 2 really relies on step 1. So like, and we'll talk about how this works here in a second, but one of the big things that takes time is detecting the status of the radio sonde, whether it's on the ground, ascending, burst, or descending. And that's really important for our calculations, and this is what I had to fix last night. It wasn't a big fix, but it was something that was going to be a problem, and I think it's our last problem. So everybody take a picture of this, because it ain't going to get any better. We're going to erase the whole thing. So I'm going to draw you a couple parts of our API, but I need to pull up my cheat sheet here. So I'm going to walk you through the problem that I had last night. So the problem that we had last night, and maybe I can screen share this. Hold on, guys. I think I can do this. Don't go anywhere. I know I'm really clunky at doing this right now. It's my first time. I opened Discord to get an image. It tried to push the Discord thing to my phone, so I had to go over there and turn it off. Sorry. Let me I'm going to try to put a sounding up on screen for you guys. I have to airdrop it here to tablet. And then it should go. Okay. So this is our sounding from yesterday. and or no, 2 days ago. So this is basically the information. God, that looks good up there. I know it's going to be a little bit tough for you guys to see, but this is basically the information that we want. This is called a skew T. This is our hodograph, and I know when you're thinking of a hodograph, you're thinking of like a bullseye, like target practice. We're zooming into the quadrant of the hodograph that actually matters. So all of our data is in this top right quadrant. So we actually zoom into that so that you're not seeing 75% of your real estate wasted. Otherwise, 75% of this box would be dead space. So your X and your Y axis here, which are both knots in this case, which is wind speed, are labeled. We've got north, south, east, and west labeled on there, so you should be able to tell you're in the proper quadrant. It's not that confusing, but this shows us our wind speed and turning with height, and also our storm motion. So if you're looking at these, there is an arrow that starts out at the 0 point, and it goes out to about 35. It goes between 20 and 40 knots. So we could infer that that's probably 30 knots, and it's just a little bit north of this 90-degree axis here. I know you guys can't see it very well there, but it's just north of it. And yep, that's exactly what it is. 29.2 knots at 256 degrees. So 256 degrees when we're talking wind speed is the way that it's the direction it's coming from. So it's opposite of this. 256 degrees, knowing this is a 360-degree circle, is opposite of this direction. So it's just draw the line back the other way. I think it's dumb. I think we should explain wind speed in degrees that it's going toward. But just remember, 9 times out of 10 in meteorology, when it's like 256-degree winds or south winds, it's winds out of the south, or like winds out of 256 degrees. So find 256 degrees on the compass and then go exactly opposite of that. And that's the direction your wind's going. We'll talk about how the hodograph works later. That's more of a different video, but the skew T, this is the big thing. This is where a lot of the calculations we have issues with. We have them with the hodograph, but we actually omit the first 50 feet of data on that hodograph, so it doesn't usually matter that much anyway. But the skew T is important. So on the y-axis, and I know you guys can't really see this too well. I might be able to zoom in a little bit, but I don't think much. I will, once I get I'll get a better camera tripod in here. One that actually works with what I'm doing. But for now, oh shoot. Yeah, that ain't gonna work. Sorry. That's all right, you can see it good enough though. So anyway, so on the skew T, and the reason it's called skew T, the temperature is on the bottom, so you've got two axes. This vertical one is pressure in hectopascals, which I am fairly certain directly translate to millibar. If not, it's close enough. I call it millibar because hectopascal is a really, really big word, and yeah. So in our case, we go from 200 hectopascals down to 1,000, and the reason we go to 1,000, this auto ranges. So this is our pressure. Our surface pressure, which is our first plot down here, was 900 and something, 990 something. So it's very close to 1,000. If we were out in the higher terrain, like central Kansas, west Kansas, whatever, it would be closer to 900. So it's just auto ranging to basically make the most use of the chart. So we've got pressure here, and then on the x-axis, that's temperature. So this also auto ranges, so that it tries to maximize it so that the data is as large as it can be. So right now our scale is from 50 degrees C to negative 30 degrees C. When we do a winter sounding and our surface temperature is 0, it's going to shift to this whole axis, and it might be 20 degrees C to negative 50 degrees C. So it auto ranges. It's not a fixed range, because that would be a huge waste of space, especially on small screens. So the reason they're skewed is because the temperature values go up on these isotherms, which is our diagonal lines here that literally go up at about roughly a 48 degree angle in our chart. I believe it's 48.5 degrees to be specific, but the reason that they skew like this is because this data wouldn't fit on this chart. You actually can do the skew T without skewing the T isotherm, but this entire column of air, because the air gets really cold the farther up we go, will start to bend back, and it just won't fit on the chart. There's also some other reasons too, but that's one of the big reasons. That's kind of like the non-science reason, so to speak, because for example, you can see here as we go up, we get significantly colder. So the way you read this is you take a point. So let's say we take this point here, and you want to see the temperature, which is the red line, in degrees Celsius. You follow the isotherm down, it says negative 20. Okay, negative 20 right here. Now, if our surface temperature is, it says 20.8 C, so we've got roughly 20 degrees Celsius right here. And then up here, which is almost directly vertical of it, is negative 20. In this first 400 millibars, this point would be all the way over here, and we would already be off the chart, and we would have to have a huge chart. So that's kind of the layman's way to put it. There's also altitude here, so we cannot directly correlate pressure to altitude. Pressure, density, high pressure systems, low pressure systems, whatever, this can actually vary some, and also terrain and topography and such. So we actually look at the GPS elevation on the radiosonde and we plot it. So here at 900 it says 1 kilometer, 3 kilometers at 700, 6 kilometers at about 475, 9 kilometers at about 320. And we just mark 1, 3, 6, and 9 because those to us are kind of the most important. So if you're ever looking for like an actual height that you can really make sense of, you can actually look at the kilometer values, which I know you can't see right now. In fact, you guys actually can't even see this. This is a sounding that's in beta that will be released as soon as I get done with this stream, probably, and how this system works. But we also mark a couple of things. Like up here, we have a tick mark for the EL. That's the equilibrium layer level. That's basically our storm top, which is up here at about probably 10 kilometers, about 250 millibars, right about here. That's basically where the rising air is not going to rise anymore. It's the same temperature. It's not going to rise anymore. All the energy for the storm is done. That's how tall our storm could be. Doesn't mean how tall our storm necessarily is going to be, but that's basically how tall it could be. Sometimes you can have an overshooting top on a thunderstorm, and that's basically that little like hat, that little bubble on top. You know, we'll pick it out next time we see one in 10 months at this rate, but that basically is that's shooting over the top of the equilibrium level. So there's a few things going on here. So the green line, and I know that's a lot. We'll actually do a detailed review on how to do this later, but the green line is our dew point. And this is kind of a shitty example because this example is a really tropical sounding where the environment is saturated. So we're plotting the dew point temperature with height, and we're plotting the temperature, the actual temperature in red. So red is temperature, green is dew point, green for rain, rain for moisture, whatever. So you'll see here as we go up, you can probably notice that the green line or the dew point line starts going a little bit off to the left. And if we follow that down in the isotherms, we're getting lower dew points. Like negative 10 dew point is drier. So dew point is, you know, the point at which dew would form on the grass, basically. So the temperature is getting lower, meaning that there's less moisture in the air. So you can see up here we have drier air than down here. But one thing you have to notice is because these lines are skewed, while these temperature profiles look like they're vertical, they're not equal, because as we go up in height, we're moving the isotherm, we follow it down closer to the temperature. So for example, right here, if we diagonal down from this point, it's 20 degrees Celsius. And I know we're too far zoomed out for you, but if we go up just that much on the chart, it's 10 degrees. There's a 10-degree difference, although it is vertical. So vertical does not equal equal because we are skewed about 40 to 50 degrees here, and we have to follow back down. That's also why it fits on the charts, like I said a second ago. Otherwise, this would all bend back like that, and you would never be able to make sense of any of this. The other line that we're ignoring right now is the line that I lack the ability to explain in normal people terms. I'll work on this. But this is basically our best way to put it. If we took air, theoretical air, ever so slightly corrected the temperature on it with an algorithm and allowed it to rise. And the reason we correct it with virtual temperature correction is because the higher we go, the air behaves a little bit different when it dries, a little bit of cooling, and it's just to make it more accurate. It's not necessary for sure, but it is making it more accurate. But basically, this is our parcel path. So surface-based, in this case, is surface-based sounding, or parameter calculation anyway. That is the path, and I say path loosely, and I'll tell you why in a second. That's the path that this parcel of air is going to take as it rises. I say path because that's the general way that people say it in meteorology, but I don't think that's a good way to put it. I think it's misleading, but I don't have a better way to say it. Now, the reason I don't like path, because to me, path infers that it's going to like curve or something. Like this visually is not how it's going to look. It wouldn't look. Like if you could somehow trace how this air is going up, it's not going to go like this. This is not a vertical column of air. And I know I'm throwing so much at you right now because look at the photograph. This is our wind speed and direction with height. Notice how it goes all the way out to 80 knots. This is this is very, very similar to the flight path of the balloon because the balloon itself is tracing the wind. So this is very similar to what our balloon path looks like. If you look at the balloon flight from Mississippi 2 days ago, that's basically what it looks like on the map. That's not a column of air. This is not a single dimensional point. We're not taking one vertical plane and sliding up and down it. It's three-dimensional space. We are ascending and we are going a distance. So we have a vector. We have a magnitude or speed and a distance or direction rather. And it also can move in a circle. Like it is a three-dimensional space. It's not a one or a two-dimensional point or plane where we can only go up and down. Sorry, I misspoke for a second, but it's not like it's a two-dimensional plane where it's a flat piece of paper and we can only go up or a one-dimensional plane rather, where we can only go up and down like a line. A line would be an example. We're not just going up and down, we're going up, down, side to side in three-dimensional space. So this reading up here might be 50 miles downwind of this reading here. So this is a little bit misleading, and that's the thing with these observed soundings. You're never, unless you have perfectly stable atmosphere with nothing happening, which is like never, you're never sampling a perfectly vertical column of air. So it's not misleading because these algorithms understand that. And when we read these, we know that we're not looking at a tube of air. But it's something it's something that was never explained to me when I learned this. I didn't finish my degree, and I probably never will. But this was never explained to me by any of them. Those professors that were paid, no offense to any of you guys that are, but like the people that were paid to teach us, they didn't explain this like that. You know, this is misleading. It makes you believe that you're sampling a vertical column of air. You are. And yes, that column is bending with the wind or whatever. It depends. You know, we can split hairs all you want, but this is not like we're just sending a balloon straight up, and this is exactly what it looks like going straight up because each reading is farther and farther downwind. The stronger the wind that it gets into, the farther it's going downstream, and we're actually sampling the same environment basically, but it is not a vertical tube of air. And I wish somebody had explained that to me 9 years ago, because when I was trying to comprehend this, I could never comprehend these. And if somebody would have told me that, this was something I just figured out how to explain a couple of years ago. I'm like, you know, this is how we should explain it. And when you start thinking about it that way, it makes sense. So hopefully that makes sense to some of you guys. And if you're like, that doesn't make sense either way, well, trust me, once we get into the more advanced parameters, it's going to make more sense and why we do some of the algorithmic corrections that we do. But anyway, this part, I got sidetracked. This parcel path is basically if we just took a random piece of air and allowed it to lift. This is on the chart how it would go. There's no capping inversion. There's no sin. In fact, yeah, so there's zero. So surface-based sin, ML sin, MU sin, 0 joules. So sin is the opposite of CAPE. So CAPE is the energy that allows this to happen. CAPE is the storm fuel, basically. That is the energy or the cooler air being above the warmer air. We all know that warmer air and warmer water rises. Cooler air and cooler air sinks. Cooler air and cooler water sinks. It is misleading to say that warm air rises and cold air sinks, because it's actually warmer air and colder air, because you could have a negative 30 degree Fahrenheit piece of air and it's still going to rise over negative 31 degree, even though it's not warm. So cold air still does it, but the warmer air, even if it's by that much, is going to rise. And that's basically where we're getting our CAPE. That's our energy. On these charts, it's actually shaded in red. So the difference between the temperature of the surface parcel and the actual temperature observed in the atmosphere, which is the red line, is our CAPE. And there is nowhere here where we have an inversion. And an inversion would look like the red line kind of jagged out and the parcel line went through it. That would be an inversion, which sometimes that's our cap. Sometimes we get through it, sometimes we don't. What the frick? Hold on. I think that's my cue to talk less. Sometimes we get through the cap, sometimes we don't. It is what it is. There's no cap here. There's nothing inhibiting thunderstorms. And you know how we can prove that? The sounding was taken in the middle of a thunderstorm, a tropical thunderstorm. And that's, you can tell because the green line and the red line, they're super close together. There's a lot of moisture in the air, very humid. You could probably argue that the storm tops were probably somewhere right around here, around 600 millibars, because that's where it finally starts to dry out a little bit. And then you get a little more natural looking sounding. So there's a couple of other things that get marked on here. The LFC, which is the level of free convection, and then the LCL, the lifted condensation level. Level of free convection is going to be that spot in the sounding that the computer says, hey, this is where the parcel path intersects. This is where we're going to get convection or the storm. That's our storm base. So we can look at that, which it's not plotted on here because this is a fully saturated sounding. Our surface temperature was 20.8 C, and the dew point was 20.7 C. It was raining. It was foggy. Like, it was nasty or hazy. It was wet. I mean, it was a fully saturated air mass. Like, if there were, the clouds were basically on the damn ground. So it's plotted down here, but it's so damn close down. You can't see the detail, especially zoomed out. But the lifted condensation level and the level of free convection are things that we look at. And we'll explain the difference between the two, but it's kind of a similar principle where one is going to be our cloud base and the other is kind of where we actually get that unimpeded growth of a thunderstorm. And I don't really have a good example on screen, so I'm not even going to try. It's just going to be too abstract. They go along with our equilibrium level. There's a couple of other parameters here on the other side of this. So we've got our lapse rates. 0 to 3, 3 to 6, 850 to 700, and 700 to 500. I probably should change those to kilometers. But those are our lapse rates, which is basically that temperature difference with height. We'll talk about those later. And then the kinematics. We have 0 to 5, 100 meter shear, which was 10 knots. And we can actually read that on the hodograph. These hodographs are easy. They're way easier than this, in my opinion, because you're just talking wind speed and direction, and then it's just subtracting numbers to come up with shear. It's really easy. We'll talk about it some other time, though. And then we actually had 58 knots of 0 to 6, and I can tell that just to give you a preview. Here's our first wind point, and it's somewhere right around maybe 5 knots or so. And then here's our last one. Let's see, the 600, so right here. It's about 55. Yeah, so there's about 50, and it says 58. So yeah, we look at the numeric value on one of the axes here from our first wind point to our 6 kilometer mark, which is the end of the green. You just can't see the point. And then we say, hey, it was, I don't know, 63, and here it was 5. Subtract them, and there's your 58 knots of shear. This stuff's really easy when you understand this, and I am frustrated because I think a lot of weather entities don't explain this the way they should. So I'm really good at explaining this in normal people terms. The reason I'm showing you this is because we need to understand this to be able to talk about what I'm about to talk about with our API. So the values that the API calculates are the thermodynamics, the lapse rates, and the storm motion. And these composite indices like SCP, which is supercell composite, and STP, significant tornado parameter. We'll talk about those in a little bit. It's just an algorithm, a little iffy. But the thermos we have to calculate. The kinematics, it basically just reads the chart. We could manually calc those easy. It would be really difficult to calculate CAPE manually because we're in joules per kilogram, and here we're in temperature degrees C. And I'm not a calculator, so. But these thermodynamics up here in the shaded area, the CAPE, that's really important because that oftentimes tells us if we are or aren't going to get convection, things like that. And we, unfortunately, we're not calculating that properly. Things like that. Let me see if I can pull up a sounding that has CAPE. Let me see, guys. If I got a sounding with CAPE, I'm going to bring it up. Here we go. This is a sounding that hasn't been put through our new sounding generator, though. And when I say new, I'm talking about the one on the screen. So you guys can't access it, but I can. We haven't publicized this yet. I'm going to share this and drop it on the screen quick. Any day now. Okay, that's cool. Maybe not. There it is. Okay, so here's a sounding with some cape. I zoomed in. So you'll see here, you see this? We've got this little inversion. So our temperature as it goes up just got warmer right here. This was from the Southeast Missouri event that we had back in, was that November? It might have been November. It was like the last storm that I actually saw that wasn't a piece of turd. Here's our parcel path, black line coming up. It goes through the temperature line. Up here we're shaded red because there's cape here. We've actually got some cape right here where it's shaded. But here it's shaded blue, that's our sin. So we've got a cap here and a cap here. I believe that this cap here is actually not a cap. I think we sent that up through the clouds. I actually think this was our lowest little bit of cloud here that it went through. It cooled a bit. But this up here, that's our sin, that's our cap. And this cap can be overcome. That's not a huge cap. I had a lot of people that were like, oh, stout cap. Not really. We can overcome that. Look at the whole sound here. There it is right there. That's not that big of a deal. We can get through that. Sometimes you need that. But this is a better severe weather sounding. So this shows all of our parameters on it. So we've got our lifted condensation level. That's where clouds form. LFC, this is our level of free convection. Draw it across right here. You see the parcel path you can see right here because the parcel path crosses the temperature line and then it's unimpeded. It's got access to everything. So we have capping below 700 millibars and above 825 millibars. But between 700 and 825 millibars, we have this cap. We overcame the cap that day. We had a big supercell, a really pretty one. This cap can be overcome. It's not a big deal. But you'll notice on this more traditional convective severe weather sounding, not that Dixie Alley tropical crap, look at how far away the dew point temperature is from the red temperature line. Look at all this dry air in here. So it's really saturated here up to about 825 millibars. I would be betting you right here at about 2 kilometers is probably the top of that rain shower. There was a weak thunderstorm rain shower thing, just popped up. It just popped up. I mean, it probably was sitting right in this vicinity of 1 to 2 kilometers. It wasn't very big. It looked like you could fly a helicopter through it or fly your drone from the bottom and be at the top in a second. So I'm willing to bet right here is where we exceeded that cloud that just formed that we launched in, and then it dries. See, we're moisture saturated. Clouds are moisture, and then it dries way out. And that's our severe weather sounding. That's a better example right there. There's not a lot of cape in that sounding though. There is, but there isn't. It's skinny. Let me point that out to you. So when we're looking for a lot of energy, I'll just zoom in one spot here. We would want to see this parcel path line, this black dash line, be way the hell out there. You'd want to see a lot of shaded red. You want a big gap between that parcel path, which is like your potential, so to speak, and then your actual temperature line, because that would indicate more potential for severe weather, more energy. So that's kind of a look at that. Now I can get into explaining to you guys what I was going to explain to you. Sorry. All right, so here's why this is important. Here's our API. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate in the back 40, so to speak. Let me, I'm going to zoom in. Let me show you. So this is all the stuff that we have to calculate Let me try to pull this up. But basically, so what our API has to do, we can't calculate any of those parameters at all unless we filter the data. So I'm going to show you guys, oh boy. I don't I don't know what's open in my browser right now. It doesn't be nothing bad, but it could be embarrassing. You never know. Nope, we're good. I'm going to show you guys in just a second. I need to open in Chrome. Oh, I can't pretty print it. Are you kidding? Shit. Well, I'll just have to screenshot it. I can't. I thought I could pretty print on Chrome on mobile, but apparently not. What a shame. That's okay. I'll just airdrop it, put it on the screen. Okay. So this is what our data looks like. This is our raw data on the API. So basically, this is what the ground station is telling the server, and this is how all the calculations are performed. So at the top, we have our SOND ID. So this one was IMET Intermet 382AB149. It's just a random string that's the serial number of the SOND or whatever. Launch count 640. So that's our frame. Every piece of information that comes in gets assigned a number. So we know, hey, this was frame 640, data point 641, data point 642. Puts them in the right order in case there's an issue with the time. Date time, so we go year, month, day, time, hour, time, minute, time, seconds in Z. Latitude and longitude, that's self-explanatory. Altitude, this is in meters. Temperature in Celsius, -9. Humidity is a percentage. The SOND does not tell us a dew point. I am freezing. I gotta turn this heat on. Hopefully this doesn't, I'm gonna put this in noise cancellation. So hopefully you'll be able to hear me over this. I am freezing. We're down to like 60 in here now. But we actually don't get dew point off of the SOND, we get humidity. So we have to calculate that in the server. So pressure, wind speed, and wind direction. We calculate wind speed and wind direction based on GPS points and the delta between the two. And then dew point is calculated on the server. We look at the temperature, the pressure, and the altitude and verify, and then we get a dew point. And then we've got our SOND event, which is cut off. It says balloon ascending. That's the problem we were having, where everything was getting marked as balloon ascending, even if it wasn't. Where everything was. And the problem with that is, guys and girls, so here's what our tracker is, right? But the problem is we would run calculations here to remove dirty data, but we typically had it programmed. Well, I had it programmed so that we omitted the ground data, because the ground data is not part of the sounding. It's not part of the atmosphere, right? The ground data is... Oh, wow. You can't hear me over the thing. That's good. But we don't want ground data, which... Can I zoom in on that? This is our ground data. From 1253 to 1257, I'm moving around. See, our temperature is wiggling, wiggling, wiggling. I'm moving around. I'm holding the SOND. We're tying it to the balloon. We're doing whatever. This data cannot... It just refreshed. That data cannot go into the sounding because that data is going to be warmer or colder or something. It's not a representation of the atmosphere. We can't have that go into the calculations. The same with the descending data. So once we get to about this point, it's descending rapidly. So this is our sonde tracker. You can get this on our website. This bottom graph is our altitude. We reach 71,000 feet and then it drops like a rock because it's falling, obviously. It falls faster than it rises. That data, we can't use that. It's going to be duplicate. It's not going to be, is it monotonic? It might not be the right word. Monotonic, monophasic, monotonic. Is it monotonic? There's got to be somebody in the chat who knows. Is it monotonic pressure? Where we only want rising pressure in the sounding. We still want to track it, right? We want to know where it's at because it's fun. Once the balloon bursts and the sonde starts to fall down, we're done with it from a science standpoint. But we'll still track it because it's fun. But we can't run it in any of our algorithms. We can't run it for data. It's dirty because there's a few reasons. Number one, we're going to get duplicate pressure readings. So we're going to come back down through the atmosphere and we're going to get pressure readings at pressures that we already have readings for. So we've got, we rose from like 200 meters or 200 or 400 feet all the way up to 70,000 feet. We're going to start getting readings that duplicate all of those heights and all those pressures, but it's going to be different data at a different time and a different place than the sounding took place, which was the ascent. That's like having two different soundings. Now, some people might be like, well, isn't that useful? You can have one sounding and then another back to back. No, it's not, because this data is dirty. And if I can zoom in on this, which I don't know if I can, I think it'll force refresh me. It'll make sense why we don't do that. Let me see if I can zoom in. So before it refreshes, look how clean this data is. This is ascending data. Look how clean it is. Yeah, our wind speed is a little bit all over the place because the thing's moving around. We smooth this. We average it out. We take averages. But look at how clean this data is. We got nice lines, little fluctuations, but nothing crazy going on because it's ascending at relatively a pretty stable and controlled rate. Now, look at this crap. This is descending. This is the same height in the atmosphere that we just looked at. It was smooth as silk 20 minutes prior to this burst that we just looked at. Now we're in the same piece of the atmosphere, but we're descending, and it's all jagged and all over the place. This is bad data. This data is not representative of the atmosphere. Reasons being, number one, by the time the balloon bursts, the batteries might be starting to get low, and we have bad sensor data. Number two, when that balloon bursts, that parachute doesn't always open right away. The air is too thin. This thing is just falling, and it's a mess. It's tumbling. The pressure readings are going to be goofy. It's not a controlled situation. Also, when this thing is descending, like I just kind of touched on, it's falling at a kind of a. It is slowed down by the parachute, but how much is very dependent on many factors: height, air density, wind, things like that, moisture level, or is it going through a cloud? Is it getting rained on? We can control the rate of ascent much easier. We can pretty much target that 5 meters per second and know that we're going to get, if we don't get 5 meters per second, let's say we get 6 or 7 or 3 or 4. We might not have hit the ideal mark, but we're still at least going to hit a stable mark so that we are controlled. So that's something to kind of keep in mind too. That's why we can't run descending data, and that's why we have to filter it. So how do we filter that? Okay. Well, I'm pretty smart, so I came up with this method. So let me pull up my notes. I said, all right. Back to this again. I said every piece of data. This is one piece of data. This is 1 second of data. Every time we have a piece of data, we're going to calculate on that server what's happening. Is the balloon ascending, going up? Did the balloon just burst? Is the sonde falling, like going down? Is it done? Or is it on the ground? So we've appended this this flag called sond_event balloon ascending, or so we have on ground, balloon ascending, balloon burst, which happens once. It's our max altitude, and then sond descending. When we plot that skew T and actually come up with our meteorological data, we only look at the data that says sond event, balloon ascending. We don't look at on ground, we don't look at burst, we don't look at sond descending. Only balloon ascending. That is the data that we want. And then we clean it, we smooth it, we average it out just a little bit so it looks nice. And that's how we get that. But to get that, and hopefully this PDF is, of course not. It hasn't downloaded. Okay, stand by. Okay, I have to look at my notes because this is complex. For ascent, which is going up. So for going up, we have to find the launch point. So we have to determine if the sond is on the ground and just moving around, or if it's actually being taken by the balloon. Now, somebody's going to get smart with me and be like, oh, just look at the altitude and look for an altitude change. Correct. That's how we used to do it. It was wrong. Wow, this is a solid table, guys. Damn. It was wrong. Remind me not to get pissed off and punch this thing. I'll break my hand, but it was wrong. Reason, I need a battery for this. Shit. I'll get one in a second. Reason, these are super accurate GPSs. I turn the sond on right here. Let's say the elevation is 10 meters. I walk outside and I walk up the hill. The elevation is now 15 meters. The sond is not in the air, but the algorithm says, hey, the elevation's increased, it must be in the air. So it was plotting a lot of our ground data as ascending. It wasn't a huge problem, but it was going to be a problem if we didn't catch it. So I'll show you how we overcome that. Let me see if I can take this battery. I think I can. You might lose audio for 1 sec. How you didn't have any audio at all. Like, that makes no sense.
That makes no sense.
I don't know why would it do that? Well, that's stupid.
I don't know why would it do that?
That's just dumb. It makes no sense. Okay, well, you didn't miss much, so I apologize. Oh, thanks, Paul. So we look for the ascent. Hold on, I gotta check something, guys. I'm so sorry, guys. That was not cool. What the? I don't know why that doesn't make any sense. Why it did that? We still good? Yeah, it said we were good when I tested it. So anyway, so basically this is how we calculate Ascent. We look for 10 consecutive points in a row. That's what I was just telling you guys right there. That have at least 2.5 meters per second up. So that eliminates me walking my my sond around or going up a hill. We look for 10 points where the change in elevation or altitude is at least 2.5 meters per second. But that's not enough filtering. So then, and we validate it with a sanity check. So we look at the first 3 minutes. So we look for 500 meters change in 3 minutes. So so the first thing the computer does, it looks for 10 points that have a rise of 2.5 meters per second. Then it says, okay, have we reached 500 meters? If yes, has that occurred within the past 3 minutes? If not, it checks again and keeps checking until we satisfy the 500 meters of altitude. Then it goes back to the last stable period. So it goes up here, which is really where which is actually our takeoff. We'll call it takeoff. I feel like that's easier. Takeoff actually occurs up here, but we're running our checks. So here, it looks for our last stable measurement where at least 5 points are roughly equal to within the same like 2 meters, basically. So again, data's coming in. The computer, once we get at least 10 points of data, it can run this. It says, okay, do we have at least 2.5 meters of 2.5 meters of vertical ascent or positive change, positive rate within the past 10 points or, per second. And if that is satisfied, then it says, okay, have we gotten to at least 500 meters within 3 minutes or 5? I'm sorry, have we? See, I told you guys wrong. I got to go back and redo this bit. It says, have we gained 500 meters in the past 3 minutes? Not are we at. Have we gained 500 meters of elevation or altitude in 3 minutes? If yes, the computer goes back before it started measuring and noticing the change and looks for 5 points. The first spot that it finds 5 points closest to where it began this check, where the data is within like 1 meter, that's our surface observation. That's our launch point, and that's where it marks the surface observation, the surface pressure, the surface temperature, the surface dew point, surface altitude. Basically calibrates the algorithms, and then it starts marking everything from the takeoff point. So it starts marking all from right here. It marks all of this then as ascending. So it changes it from on ground to ascending. And then everything is ascending until we get to the balloon burst. Until we get to the balloon burst. So the first thing we look for is max altitude. Now this is easy. So every time a data point comes in, our CPU is running the same calculations over and over. So as the balloon is ascending, it's actually always satisfying this max altitude thing, unless it's descending. So we're always at the max altitude, but this is kind of like a Boolean thing. We have to know this value to plug it into the calculations. So we have a max altitude. Then the computer goes and checks and says, hey, is there a point where it drops below? So let's say that our max altitude, it's running a calculation and we're at, I'm just going to use easy numbers, 50,000 feet. the computer says, is there another point in the database where this sonde on this flight is below that altitude? Well, yes, because everything leading up to it was. But there is a flag with that. Some of you guys were going to pick me out on this. So we'll use that to filter out later. But so it looks for, is there a point that is below max altitude? Yes. Is there a point that is at least 100 meters below max altitude after it found max altitude? So I know this is a little confusing. So it looks for 100 meters below the point after it believes is max. It's hard to explain. We get max altitude. It says, okay, 50,000 feet. Is there a lower point than that? Yes. Is that lower point at least 100 meters below it? Yes. Is it after max altitude? Yes. The balloon is burst. Well, a few other things. No, if not, it stops the calculation. The balloon is still ascending. It moves on. There's one more thing that gets there's one more flag, if you will, that gets satisfied. Then we run a check. Does it recover? So the reason we don't just flag it as burst the second that we get 100 meters below the highest point is because what if this thing is a bad launch, a goofy launch, it gets caught in like some sort of downdraft current, and the wind or precip or something or icing forces this balloon to descend a couple hundred meters for whatever reason. Unlikely, but it can happen. It's an edge case. The algorithm says, does it recover? So it will, before flagging it as burst, it will look at more data points. And if it never, ever, ever recovers, so if this altitude here, if that never, ever meets or exceeds the max altitude, which in our example was 50,000 feet, it marks 50,000 feet as the balloon burst. So this eliminates, if for some reason we're going up, let's say we get to 60,000 feet, for whatever reason, it could even be a data error, a GPS error. The data says that it dropped 200 meters. Instead of saying, nope, we're done, I'm going home, and marking it as burst, it looks at more data and says, did it really burst? Did it ever start going back up after that? And if it did, then it runs the calculation again until it finds a burst or we lose signal. So that is how we accurately detect the balloon burst. And then what we do is we flag everything after the burst as descending. It's done. It's junk. We don't use that data for anything scientific. We still log it, we plot it, we put it on the map because we want to track it. It's fun. But that's how we detect the difference. So wow, that was tough to explain. I don't know why. Jesus. So that's kind of that. That's what I had to fix last night, and that's how we came up to do it. That's kind of that. All right, and we still have sound. That's good. Okay, so what questions do we got here? I'll actually look at the chat this time. Definitely not a math lesson. No, not my strong point. That's for sure. But anyway, thanks for joining, guys. I kind of wanted to give a little bit of an update with this stuff. Couple of things that why is this? Oh my god, come on, freaking laptop. I just got lost. Anyway. Yeah, so like what Paul said, about the, so I don't know if anybody thought about this, but this is a Visala, Visala, whatever, Sand. I have a camera for that. Stand by. Oh no, the audio is going to be desynced. Never mind. I didn't time sync it yet, so I'll just go up here and hold it up. So this is a Visala L band, 1680 megahertz, very old. These are the ones I was telling you guys I think we should make trophies out of. Come on. I'm trying to open it. it's there we go. So they run on AA's. This is one of the ones for testing. We didn't just smash, I promise, but this is the actual sound. When you fly these, the boom gets moved like that, so it's out of the way of the string. This dangles from the balloon. So one of the things that we have to watch out for, now not this one, this doesn't have GPS. I have no idea why. But when we have ones with GPS, like our intermets or common sons, you've got like anywhere from 50 to 100 feet of string below the balloon. And as it's going up, especially at launch, it's going to have a tendency to do that. The balloon, actually, you can see it visually, like it likes to roll. They're not balanced, obviously. So you're going to have this thing swing. If you've got 50 to 100 feet of string, somebody could do the math. I don't know what the answer is, but imagine how far this thing's going to swing out. These are highly accurate GPSs. Well, just don't have them, but they're highly accurate. So if it swings 100 feet this direction, it's going to plot it 100 feet that direction and then swing back, and you're going to end up with terrible, terrible data. So with that in mind, the modern SONs, maybe not previously, they are pretty good at filtering that out. The interesting thing with Intermet, though, Intermet is I think the only SON that does not transmit wind data. The GRAW does, the RS-41 does, which are the two that the Weather Service use, but ours, the Intermet, does not actually transmit wind data at all. We have to figure it out ourselves. Or if you use an Intermet ground station or the Intermet software, yeah, it does the same thing that we're doing. But that's actually determined on the ground. So we have to look at the delta between the points on the latitude and longitude. I forgot what I walked over here for. So we have to look at the delta between the 2 points, which is the difference. So what we have to be sure that we do is we smooth the data out. We have to look for abnormalities and omit bad data, like the swinging. We look at 9 seconds of data at a time. So we have a 9-second wind resolution for direction and speed, and we smooth it and we average it. That's what the Intermet ground stations are doing, is they're looking at a 9-second smoothing resolution. I'm like, well, if that's what you guys are doing, then I'm going to duplicate it so it's the same, exactly the same. I think every other SON, the Meteo modems might not either, but Intermet, they chose to not send the wind data from the SON. My expectation or my assumption for that is likely because it makes the SONs lightweight. Because when you have more processing power and more computer power, you're going to have a heavier sand. And these are they're ultra lightweight. They're 100 grams. Very light. You know, we can launch that sucker on a 100-gram balloon and probably be just fine. So they're very lightweight, and I think that's a lot to do with it. But that was actually a good point that Paul brought up. We have to really take care of our wind data because we are the ones smoothing it. But we're smoothing it the same way that the internet ground stations do, because if that's what they're doing, they make the damn things. I'm going to do the same thing. But yeah, we have to really watch for that. Especially that's really, really a thing too at the takeoff or the first part of the ascent rate. Because when it comes out of your hand, it comes out and then it starts swinging all over. And a lot of people have the tendency to like throw it up. Like it's not, you really have to smooth it. We actually omit 50 feet to the surface. We omit that data. It's just bad. You want to buy an autographed old sand? Well, yeah, that's a possibility. I had one. What the hell did I do with the damn thing? Oh, it's. Hold on, guys. I got to go take a field trip upstairs here. Hang on. Here, I'll get you a freaking son. You want a son? I'll get you a son. I got pallets of old surplus radio sons that are no good to us, but it's cool. It's like a nostalgia thing. So this isn't going to be fully synced with my audio. Look at this, guys. My Sala RS92s, and it's even in Swedish or whatever it is. Look at this. Whatever language they speak. Dutch or something, I don't know. Look at that, guys. I have 1, 2, 3, 4, 5, 6, 7, 8. And up there I have, hold on. See, I still got 2 boxes on the porch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there's 2 full boxes. 12. What's 12 times 8? Shit, I don't even know. I have almost 200 of these things. So, yeah, if you guys want one, I tell you what, people. What I can even do is we could actually send people that might want them. We could actually send an unopened one. And then 2, so like if people don't want to open it to like preserve the nostalgia or something, you could do that. But they're vacuum sealed right there by Sala OYJ from Helsinki, Finland. And serial number, and there's a NOAA number on here somewhere. But yes, so no, dead serious, guys. Like a lot of people were like, "Oh my god, I want one of those." Okay, yeah, cool. I will get you people one. So if you guys email me, I can figure out what it's going to take. It's probably going to be a month or 2, though, guys. It's not high on the priority list, but yes, if you guys want sans, I would be happy to send you guys some of these, because that's kind of the point. Is it's kind of like a viewer activity. Because it's kind of cool, I think. So yeah, sure. Piece of NOAA history. Yeah, so we can do that. So shit. Somebody wanted to see the balloon. Okay. There's the balloon. So obviously we run different sizes of balloons. This is the KMOT 200 balloon. 200 is just the size, basically. I've got a kind of a fun little activity with this. I can't believe I just said that. Where the hell's my scale? Oh, come on, man. Where is my scale? Well, maybe not. I was going to say we could weigh it and see. It's for the hell of it. I lost my scale. Dude, come on. Are you freaking kidding me? Yeah, I need that too. Oh no, because like I need to make. I was gonna make some weights, different weights. Where the frick? Well, we're not gonna weigh it, but that's the balloon. Obviously, we have different sizes. That's a 200. It's probably gonna be our most commonly launched one. That one, that's a really good balance between cost and gas used and performance for us. Really like those 200s. So now I'm going to insert sales pitch. So folks, if you are new here and you're like, wow, this stuff is just so damn cool. Wow, I totally want to help these guys pay to launch weather balloons, probes, and a bunch of other crap. Well, it's really easy to send us your money so we can do that and better the world. And also, it's entertaining. So GoFundMe right here. We're at $11,725. And we're getting there. There's 207 people have donated. So thanks if you're one of those 207. That puts us at 47% of our goal. So we're almost to 50%. So looking forward to that. You could also learn a little bit more on our website. So if you go to project, God dang it, all the hell. There we go. The Project Weather Eye website, wxeye.org. If you scroll down a little bit, you see that this is actually a video. I know it doesn't look like it, but you click on this, click to learn more for Rise 26, and it goes to the Rise 26 page. That's our logo, which I think is cool. That's going to be on some patches that we'll have. And there's our intro again. Here's our soundings again if you want to look at our soundings. These update live. I want to mention that, guys. While we're out there doing this operation, just refresh the web page. The second that we launch a balloon, it shows up here. It's automatic. It shows up in that widget. That's embeddable too. So if any of you guys want to, if any of you guys have a weather website or like a hobbyist website and you want to embed this widget, send me an email and you can embed that in your site. It's just an iframe. So how this works is you expand it for your month and then you click on view sounding and then it takes you right into the viewer. There's your sounding, there's your data, sounding, data, sounding, data. So we talk a little bit about the 4 branches that make up our Rise 26 mission. So this is a little bit out of place. I didn't have a picture to put here, so I made some clip art. Pretty proud of that. It's supposed to be a weather station. I'm not quite sure why there's a cloud with rain connected to the weather station, but I was really tired. But we obviously, it's our upper air program, our ground-based probe network, storm scale deployments, and then the storm scale deployment team, and then our live video grid. That's kind of like our 4 branches. So we have a dedicated upper air team, a dedicated ground-based team, which is our probes and the storm chasers with the stuff on the vehicles, and then we have a team or an effort to do these deployments on a storm scale that's going to be its own dedicated thing, and then of course our live video grid, and that's going to be its own thing that needs to be babysat on its own too. That's all of these massive camera packs. Oh my god, that stream video for like 9 days straight. And also our smaller, much more portable, quicker deployment ones. This is the original one this was our original design. This was Zach's. This is number 6. And here's one of our probes. So these are very small. This is just kind of the brain box, though, so to speak. We'll talk more about how the sensor and the sensor boom and all that's going to work some other time. But this is kind of the size we're dealing with. Like, we have staff members that are going to be deploying these. And if any of you guys are watching that drive cars and you're like, no, guys, you could fit. These are no big deal. So that's kind of where we're at. Oh, also, I want to mention the blog. Go subscribe to this. Go onto our website and put your email into our blog so that I can send you spam. I'm just kidding. Understand when you sign up for this, you might get an email every damn day during severe weather season. Like I've had a few people put their email in and then they're like, "Stop emailing me." And it's like, "Well, why the hell did you sign up for it?" We haven't posted since August. That's because it was the last time we did anything organized. So during severe weather season, every day, April 1st through July 1st, there's going to be an update on this blog. We're going to have our findings from the day before and our plans for the day, and then our plans for the coming days. So these will actually get emailed to you if you sign up for it. And I'll show you an example. Like this is kind of the style we're doing, right? So we write a little blog article. We put some screenshots of what happened, video clips, pictures. We'll put the soundings and all that stuff on there too. So that's where you want to be. We've also got we're going to be posting. Yeah, I'll wait on that. That's something I'll announce later. But that's where you find that. So our website, I'm probably going to revamp the website a little bit. It's got some issues, but we'll get it fixed up. Anyway, like I said, folks, if you want to yourself get involved in this, that GoFundMe is where you do it. We definitely need your help. If you're a business and you want to sponsor this operation, send us an email because we can probably do a pretty sweet deal for you guys. We just need this is a really groundbreaking mission here that a bunch of YouTubers are doing with no budget, and I'm pretty proud of it. So. I'm probably going to be fixing to get out of here. Guys, I need to eat. I'm starving. And that kind of covers everything. We've been live for about an hour and a half. So I'm probably going to fix to get out of here. This was our test. I like our broadcast set here. There's a few things we're going to change. That television, I think I'm going to put on a longer arm so that it comes out more. And then the shelf, these are going to be switched to the back wall. But so far, I think this is going to work out really well. And then we can launch our balloons here. We got our camera on the table. God, this thing is solid. It's a hell of a table, guys. I mean, I don't even know if I can... Oh, barely. Yeah, this thing weighs like... The shipping thing said like 426 pounds or something. I think it's closer to 500. I mean, it's the freaking big table. Like, I tell you what, just I moved it all the way down to the garage door because I was sweeping. I moved it all the way down there the other day before I left, and I damn near sent it through the garage door. I think it's got some mass. All right, unless anybody's got anything, I'm going to get out of here. So thanks for being here, guys. I'll probably be back in a couple of days. I hope you all have a good rest of your evening, and we will see you guys later.